Hi, my name is John McMaster here in my Silicon Valley garage.
Hi, and I'm Yusuf, and we're Geek Moniker. So, John, today we promised the users a view into microscope software.
Here in my Silicon Valley.
What do you have for us today?
Sure, maybe what I can do is I'm going to switch on my camera here. Give me just a second, hopefully. Can you see me now?
Yep, I can see you now.
Great. I think you've seen that, you're aware of, I do quite a lot with microscopes by now, and I've got a few of them. You may or may not be aware, there's been kind of a long path to getting to kind of like the nice microscope setup that I have today. Do you by chance know some of the evolutions on that setup over time?
No, I do not. What have you done with it?
Sure. Back in college, when I first started doing this, I had a very crude setup where I just took a point and shoot that, gosh, maybe I found in the trash even, and wired up some like crazy wires to it. And I literally was using something called G code. Do you know G code is by chance to control
Um,
the camera?
yeah, it's used for like CNC control, right?
Exactly. So there are some instructions. I'm tempted to say M3, M4, M5, something like that. In any case, they were the coolant on and coolant off instructions. And I wired up the coolant on and coolant off to the shutter of the camera. And that allowed me to, by soldering wires onto what the user would usually hit on there. And that allowed me to remotely take some pictures and along with some other very crude code, I was able to kind of move a microscope around and coordinate with a camera, which works, but it's a rather crude, isn't it?
Yeah, I guess so.
Yeah. So from there, I started thinking it would be really nice if I had an industrial grade, kind of professional microscope camera that I could use with Linux. But there was a problem. Do you know by chance what the problem I ran into when I tried to do that?
Was there like an interface issue?
That's right. It turns out that there were no real microscope cameras, certainly at the time, that were compatible with Linux. At least I'm kind of a Linux guy, and I wanted to stay in that environment for a couple of reasons. And it wasn't looking easy. There's a little bit of a thing you can do where you can use, like, say, a web camera, like we have here, and we'll go back to that a bit. But long story short, those are not recommended for microscope applications. And if there are follow-up questions, we could talk a little bit more about why. And I went through this long path of reverse engineering a professional microscope camera, and I got that even into the Linux kernel. I have a driver in the Linux kernel, and that has been the camera that I've been using for a very long time, and that seems to work okay. But there's been a lot of friction, and the biggest thing is, as I've tried to do newer cameras, I haven't been able to switch to anything because I went through this really long work of reverse engineering, like an obfuscated USB protocol and all that stuff. Does that kind of make sense of what I've been using for a really long time as kind of a
It,
core?
it does. A quick question though. So
Yeah.
you said the newer cameras. I would assume the newer cameras kind of utilize more modern, USB protocols or like show up as a USB device. Is that not the case?
It is. The camera that I would like to switch to, for example, is a 12-bit sensor as opposed to an 8-bit. It's back illuminated, so it has much lower noise. It's USB 3 instead of USB 2, gives me a higher frame rate. It has a lot of advantages to give much higher quality images. The problem is, though, is that if I wanted to use that, it doesn't use the generic USB device classes. And this is not just this camera, all of the cameras are like this. So I would have to reverse engineer that camera's protocol again if I wanted to support it into my microscope framework. And that was kind of the big question, some months ago when I started thinking, how am I going to modernize my microscope framework?
Okay. And so what did you come up with?
Well, there are a couple of options. I could have the vendor, Tube Tech, actually makes most of the microscope cameras on the market. Most of them are just rebrands. And I started out by looking into their API, and they actually, to their credit, they have a pretty nice Python API. The C++ API isn't bad either. And I was able to make some quick applications, and maybe I could have integrated everything together. But if I did that, I was going to have to move away essentially from my existing GStreamer pipeline, which I use today. So GStreamer is a multimedia framework, which handles things like video rendering, selecting between, say, a webcam and some other proprietary USB device, and allows you to kind of aggregate all those video streams together and process them into, say, a microscope application. And I started thinking about different options, and it looked like probably the best, like most proper, would be to write a C++ that is a low-level programming language, a little bit cumbersome but relatively fast, and that would allow me to write a very fast plugin that would go into GStreamer, use this vendor's proprietary code, and by using this proprietary library in collaboration with an open source framework, GStreamer, I would be able to support all of the cameras that this vendor supported without having to reverse engineer all of them. So at the end, it's not this pure open source application like I had before, but it was kind of a compromise to get a lot better support into the microscope framework.
Okay, and is that what you went with?
That's what I went with. Yeah. So I got some help writing a C++ I got someone to help me write an initial version of a very basic GStreamer C++ program for this microscope camera. And at that point, I was able to do some very basic, like snap a picture, using some stock GStreamer tools. But in order to actually make that useful, that then needed to be integrated into my normal main microscope application. And this is where we start running into problems. You know why?
Why?
Because that code was very, very old and very hastily written and just honestly extremely poorly maintained with hacks everywhere. So as I started bringing in this GStreamer stuff, it also was just kind of time to say like, hey, there's all this legacy code in here. It wasn't great code to start with. I just kind of need to do like a major overhaul of everything. And that's kind of where we get to today. Is recently after this GStreamer plugin kind of matured and I said I would like to integrate it, I did a major overhaul of the microscope software. And so maybe at this point, I can bring you up kind of what the relatively modern version of that software looks like that I use for my chip captures and show you just roughly what it does. Does that sound good?
Yeah, sure. Let's have a look at it.
So I'm going to stop the video here. And I'm bringing up my software. I'm going to share my screen with you. Okay, and hopefully you can see this over here now, roughly.
Yeah, I can see you.
Great. And one of the design goals of this software versus the previous version, I would describe the old version as kind of a programmer's GUI. Like it was this wall of like buttons and fields, and like there were just, controls everywhere. And that just kind of made it hard to use for various reasons. What this new version does is it just has one very specific goal it tries to accomplish better than anything else. Set up an area of a chip that you want to image and take a large panoramic XY scan over that area. So you need to specify basically a start location where you want to start imaging, an end location where you want to finish imaging, and a few other imaging parameters like how big is your field of view over the chip. And as long as you have that, it has an imaging device, and maybe you give it an output file, it's going to do a large scan where it might take, say, 100 pictures of a chip or other sample. Does that make sense?
Mm-hmm.
Okay.
Yep.
And the only other thing that I threw in here was I did throw in a very basic snapshot functionality. So at a high level, that's kind of what this software does. Does that make sense so far?
Yep. Seems fairly straightforward.
Okay. And the other thing you see here is this region of interest view. And what that allows me to do is focus on samples a little bit easier, because this is on the left is a very zoomed out view. And if you're trying to focus on the very minute details, sometimes the screen just doesn't have enough resolution to show everything that the chip has. So this allows me to select the focal plane and get the best quality chip images.
Okay. So is the overview what the camera is actually seeing and the focus is just your digitally zooming in to
That's
that
right.
image?
Yes, that's a digital zoom.
Okay.
Yeah. And one of the important things here is I am, for example, using a webcam source, which is supported by the GStreamer framework as a generic USB video class, or they call UVC, you might hear that called. But I'm not on an actual microscope here, but if I was, I also could have fed in one of these microscope cameras, of which there are many on the market, and this framework now supports. And so since this rework, and also the code has been a lot cleaner, I've also been able to start doing things like trying HDR support. Do you know HDR?
The high no
Close.
HD
High.
dynamic range.
Yes, there we go. Yeah.
There we
So
go.
now because the code is a lot cleaner, I've been able to do these sort of experiments. One of the long-standing issues with my framework, or as I image chips today, I should say, is if you have some metal which is very reflective, you get some bright white that comes off of that. But some other parts of the chip, which could be most of it, which aren't as reflective, you just lose a lot of contrast. So one of the experiments with this software was trying new things like, can we actually do multiple exposures per image and therefore see both the darkest and the lightest parts of the chip and get much higher quality images? So far from that perspective, this new software has been enormously successful in that it's let me run these experiments in kind of a quick manner to try new things to get better chip images.
And like the HDR and other kind of transform that you do on the images, is that happening in this particular software, or does this software just capture the images and you do it off board?
The latter, yeah. I've tried to do as little processing as possible in the software. That way, if you want to try different HDR flows, you can post process the data differently to get those results.
Okay, very good.
Yeah.
And then how long have you been using this?
This new version, I think, has been in use for maybe a month or so. One of the big trials that it has coming up is I posted an image of a high resolution objective on Twitter recently. The idea for that was to do a very high resolution scan of the so-called PPU chips, or the picture processing unit chips. Unfortunately, I am missing an adapter to do that right now, so I'm holding off a little bit on that. But one of the core things about this new software is I'll be able to use a higher quality camera to do those scans, as well as I don't know if I can do a scan easily here, but there's some like pause functionality and stuff like that, which is also going to make those very large scans a lot easier.
Okay,
So
sounds
yeah.
sounds good. So it seems you've got a like good handle on the basic core functionality of this app. Like, what are some of the things? You said this was an open source project, and people can go look at it. The
Yes.
links are in the description of the video.
Yep.
Like, what would you like to see happen with this? Right, where would it go? What can people contribute? Maybe.
Yeah, I would say right now there's actually been more interest than I was expecting, frankly, for this framework. Between the GStreamer plugin itself and this, I think I've had maybe 5 people who have used this so far, which is honestly way higher than I was expecting for a project like this. I thought this was too niche. Um, I'll start by saying what are the contributions I've gotten so far. Most of the contributions so far have been on the GStreamer plugin itself. In particular, there's been a lot of interest because there's no support on Raspberry Pi from the official manufacturers for GUIs. So I would say that's been the one use case there's been a lot of interest in, and maybe I would expect to see some sort of pull requests related to that and whatnot. Other than that, I've also had some limited use cases, people using the same framework for like X-ray scans and other stuff like that. I would say that it's going to be, based on the individual use case, what people are interested in. But as long as you have a use case, which is I need something that knows how to do a large panoramic scan and collect data, this is kind of a generic framework to do that type of work.
Okay,
Um,
very
yeah,
very cool.
depends on the other user, I guess.
Okay.
Yeah.
That's cool. And you said that a few people have tried this out. If anybody wants to kind of share the images that they've captured, just tweet us. Tag us at Geek Moniker, or or you and me,
Sure.
and we'd love to see them.
Sounds good. I was thinking maybe as one quick last follow up, unless there's any questions about this, I could also briefly touch on the 3D prints we did recently, which also tie into this.
Oh yeah, definitely. Let's go ahead and have a look at those.
Yeah, so I think we talked about them a few weeks ago in a little bit of detail, or Did we talk about them a little bit?
I think we mentioned that. We
We
mentioned that
mentioned that.
we were printing those adapters.
Yeah, the basic idea as part of a microscope retrofit project, these are the linear stages I use. Hopefully there's enough light here you can see this. And the problem is, I'll tell you what, let me switch back to normal camera view so I can show these a little bit easier. Just stand by for just a second. Hopefully I can start this camera up. Oh,
And the
it,
lin oh,
still,
go ahead.
okay, how about now?
Yeah, I can see you now.
Great. So the basic idea is there's a gearbox that was previously on here. I think you can see these little sticks sticking out. That's where a planetary gear used to be. There is an adapter that has been 3D printed, which goes into that planetary gearbox. And hopefully I can slip this on here. And the basic idea is the old motors on these linear stages had a lot of issues, ranging from just being very generally difficult to control to also just having a lot of play in this gearbox. By putting this adapter on here, and there's a little housing that goes around it, which you can put basically here. And then that housing connects it to a stepper motor here, which fits on this if I rotate it around. You can see roughly what the idea is right here. That allows me to use these old, very high quality linear stages, which are relatively inexpensive on eBay for the quality that I get, and bring them to kind of a modern control system. So this is kind of a work in progress on the microscope right now, and once fully retrofitted, it should increase the quality of the scans a little bit.
Yeah, very cool. And it was maybe like 5 or 6 hours to print those things. I mean, 3D printers have really changed, what people can do at home.
Is it each one of these was 5 or 6 hours?
Yeah, I think that particular one was about 6 hours because we actually printing it completely 100% infill, right? It's a complete solid part,
Sure.
and that was just overkill in terms of structure and flex, etc. I mean, I'm sure we could have gotten away with a lot lower infill, but it's hardly anything, right? It's just maybe an hour or two extra of time, print time.
Well, I think that's all I have today, unless you have something else to add.
No, I mean, that's great. Do you happen to have any pictures that you have captured from this? Any like test pictures?
Oh, I mean, this is already in production. So if you've seen any of my relatively recent microscope captures, they are already from this project. One that I could bring up, maybe if you give me a second, I captured a chip recently, which was one of the HDRs. If I could actually bring that up, that would be a nice example. Let me see if I get that up. Also, we should check to see if there are any questions on YouTube. I don't know if you've been monitoring that.
I have not as of yet.
Okay. From this project. Let me see if I can find that then. Do you by chance remember that? I don't remember if it was a Nintendo chip exactly or what it was.
I do not. And we could actually just add the links to the description as well if people want to go and have a look at kind of what you have been capturing.
Yeah, that may be easier unless I can find that really quick right now, because I don't know if I have it handy. So,
And as you're pulling it up, I actually do have a question. So as it scans across the chip, capturing images, right?
Mhm.
How like is it a very clean like partition, or do you have overlap between the images you can like how I guess accurate or controlled is the XY kind of pan across the chip?
I would say there's a couple of factors on that. The biggest limiting factor traditionally has been that my microscope optics have a lot of distortion. And as a result of that, I try to add something like, gosh, maybe 30% of overlap or more with the on each side. So that's 60% overlap total, which is I would say is relatively a lot. And part of the reason why I do that is to make it so that the center of the optic, which has the least distortion, gives one of the higher quality bits of image, if that makes sense. Essentially, you're essentially zooming into the center if you're getting a lot of overlap between adjacent images.
Right, right. And how do you stitch it? Is this like something you throw it into an app and it stitches them all together, or do you have to manually go in and kind of rearrange the images?
I have my own special framework essentially for doing this, and I think that could be a whole episode by itself, although we could talk about it a bit here.
Sure.
The high level overview, though, is I am loosely based on Pano tools. If you're familiar with libpano and whatnot, it's the same core that's used by Hugin, except I am making a lot of assumptions about this being a planar XY scan with repeatable positions, as opposed to Hugin, which assumes, hey, you could have these cameras, yaw and pitching around, they could be moving around.
Right.
A much more generic problem. And so by simplifying that problem and then also breaking it into smaller problems than Hugin tries to solve as one giant image, I am able to optimize both the memory and CPU usage to make it considerably faster than Hugin is able to stitch it.
Okay, very cool. But it is pretty much a hands-off process at this point.
It's pretty hands off. The only things that I do manually is if it does, well, assuming I give it good data. If I give it bad data, I have to step in a bit. I have to crop it, I have to rotate it. Other than that, it's basically automatic. And I've
Okay.
experimented with auto cropping, but I found it's just such an opinionated thing. It's just not worth it to try to use their auto crop algorithm.
Okay, very cool.
I can show you, since you were asking about the HDR. So here was one of the very early tests with it. Let's take a look at this to start with. Here is a conventional image from it. Do you see how this area of the chip is just really washed out?
Right, right. It's super blown out.
Yeah, and the reason why is on this chip, I think it's particularly bad. It's not obvious, but there is a protective coating over the top of this chip, and I think it's increasing some of the reflections even more than you'd normally get on chip. Like if you zoom in over here, it seems like it's not too bad. But yeah, the upper left is just really washed out. And in particular, notice how this is still relatively dark over here. So if I were to decrease the light levels for the the upper left, we would start losing detail down here, right?
Yep.
So the solution to that is to take it at multiple exposures and then try to combine those together. And that's what this one does. Is it took something like 5 different exposures at this area here, and then tried to blend them together to produce one, image that was exposed a little bit more precisely at all those different levels, and kind of, I guess it does histogram equalization or something of that sort to make it look nice. And now you can
All
see a
right.
lot more detail here.
Yeah, no, that's actually pretty dramatic. I mean, that almost seemed like it was done under a totally different process.
Yeah. But yeah, it's the same microscope, just different imaging settings and a much more intense post-processing workflow.
Okay. Yeah, on this note, like I guess you said that there's one kind of, setting, exposure setting for the whole capture, right? Since you capture individually, have you, looked into maybe having like each image that's being captured adjusted for exposure and contrast?
Well, I mean, that's essentially what this is here. The problem, though, is if I take this image up here at one exposure, and then I take this image down here at a different exposure, there's multiple problems. First of all, what is the correct exposure value? And then the second problem is once they're at 2 different exposure levels, how do you blend those pictures together so you don't get a stitching seam here?
Mhm. Yep, that's true. Yeah,
Yeah.
no, I mean this HDR thing is quite dramatic. Like it's pretty good. I guess this is what your pipeline actually helps you do is experiment with these type of enhancements, right?
That's right. Yeah. And this is still experimental. I don't know how much I'm going to do this moving forward. Most chips don't have artifacts this extreme. It does take a little bit more work to set up. And certainly, as I have the microscope software set up now, it's a little bit wonky to actually import the HDR values. So we'll see how much I actually use this going forward, but
Okay.
at least it's there as an option.
And as far as speed, like how fast I guess is one image capture, right? Like how fast can you image a chip?
I would say that if this gives you a ballpark, maybe I'm capturing 1 image a second A lot of that is actually limited by the mechanical settling time of the stage. And there's a lot of things that I can do to optimize that, but it's about a second right now, I would say.
Okay.
Um, this chip, gosh, this was pretty small, I guess I would say. This one was maybe 60 images, maybe more, if that gives you an idea. But I would say a typical chip, like say like a 6502 type chip, is going to be maybe 300. And if you get to something like the PPU, though those are relatively large chips, and that's probably going to be in the thousands. So maybe 1 to 2,000 images for those chips. Quite a bit more images. And then with the imaging time, depending on the movements, it actually may be more than a second. I should clarify. It's a second at a high magnification. At 20x, which I would probably do the PPUs at, it's probably going to be more like 2 or 3 seconds an image. And for that, it's not unreasonable to have imaging times in like the 4 to 8 hours for a chip like that. Which is quite a lot of data as well.
Right. And that's not accounting for all the post-processing, cleanup, etc. that you do.
That's right. That's right. And that has to go in that. And especially for those really, really large stitches that, I just can't fit in the RAM of the computer I'm trying to stitch that image on. That's where that special stitching workflow, where I do these things where I break it up into smaller images and stitch those shards and then recombine the shards into one large image at the end. That's where that workflow becomes also very helpful.
Okay. How big is like one image? Like what's the file size?
Oh, I mean, it depends. Like this one, we could take a look. If
Or I
I
mean, I guess even like one capture, right? Not even the whole image.
Oh, yeah, this is going to change a lot if I move to the more powerful camera. The fundamental issue is the way that the optics work out on the microscope with field of view and all this. You only get maybe 1.3 megapixels of useful information for the field of view that I get. As a result of that, I think the actual JPEG size ends up being pretty small, like maybe 300 kilobytes, I guess in that ballpark for a typical image. I'm hoping though, as I move to this newer 12-bit camera, which also has a physically larger sensor area, I also should be able to get away with more, a wider field of view, and I may actually get much more high quality images, which will also take up more space on disk. But I think overall will increase the stitching quality.
Okay. And the JPEG compression artifacts don't cause a problem, or do you just turn the compression way down?
Yeah, both of that. I would say, first of all, I do typically 90% compression, which to me, like, I'm sure if we start looking in here, yeah, we're going to see JPEG compression artifacts. Like maybe that's what these lines are right here. But even those, I'm not sure if those are JPEG compression artifacts. Yeah, I guess they are. You can see some JPEG compression artifacts here, but most of the texturing you see here, I think actually is texturing on the chip. At least from my visual perspective of quickly, looking at them like this, those JPEG compression artifacts don't bother me that much. Maybe if we were doing some machine vision stuff, it would be a little bit more important. The problem is if we store them as say like PNGs or TIFFs, they tend to take about 10 times as much data. And that would significantly increase the cost of running the site. And I'm just not that interested in paying those hosting costs right now. I would say that's the biggest leading factor.
Okay. But do you actually capture them in PNGs and TIFFs, or no?
Today, I capture them as JPEGs. However, if I move to the 12-bit camera, I will probably capture them as RAW, probably as TIFFs.
Okay, very cool, very cool.
Yeah.
So, I mean, no, I think that's been a good view. I don't have any more questions. It might be a good time to stop here.
All right, sounds good.
Perfect. Hey, thanks a lot for watching, everyone. See
All
you
right,
next
thank you.
time.
See you next time.